Oh, whoops, I didn't, I forgot to share the link. That's why no one's here. Let's see. Good morning, Mr. Ross. Oh. Woo. Oh. Hey, Chris. You saw the question. Yeah, what do you think about the question, Chris? Hi, Sarah. Good morning, Itamar. What do you mean, Chris? What do you mean? Why do you think I like paragraph answer responses to explain? Good morning, Atune. Let's start at around 10:02, all right, which is in 2.5 minutes, okay, just to let everyone have enough time to join the stream and stuff. Hey, Ethan. Itamar, what makes you say that? Now, okay, yeah, so Chris, I have a question for you, right? So I expect an answer. Why do you think I really like paragraph answer responses to explain? Itamar, I have a follow-up question for you. I have two. What makes you say that you've lost faith in standardized exams? In what way have you lost faith in them? Because I think there are a lot of different ways you can lose faith in different aspects of exams. And are the solutions available? I don't know if like what I'm about to do is helpful, especially if the solutions are available somewhere. Chris says, because they're important for the questions here. Yeah, but Chris, that's not why I do that, okay? Because that would imply that I'm teaching to a specific exam. No, I like paragraph-length responses because I think they, above all, kind of show whether or not you understand something. And I think they're great tools to get you to understand something or to get you to think in a certain way. Otherwise, physics simply just becomes like identifying like which variables in an equation are missing and like how to mathematically solve for them. And that's not what physics really is, right? Physics is like an attempt. It's a noble attempt at trying to explain things that we observe, right? And we do that via written responses most of the time. Hey, Yona. They tried to cover so much yet fall so short of so much that we have learned. It's not a final cumulative examination. Yeah, I would agree. So for the practice exam, I think they covered almost everything except momentum. And they covered everything except angular momentum and linear momentum. Does that mean that's going to show up on the exam Thursday? I don't know, right? And honestly, don't worry. Like, a big reason of why I'm doing this morning is just because I think a lot of you are still a little worried behind it about the exam and stuff. I hope that you don't worry about it, okay? I spoke with Mr. Nasser last week, and he confirmed with me that your performance on AP exams has almost no bearing and like zero weight on your eventual college admissions decisions. It's there on the Common App. I don't even know why it is, because the very fact that it's a self-reported score that doesn't have to be, you don't have to submit a college board report, score report, kind of should tell you enough that colleges don't put in a lot of weight into it because it's self-reported and anyone can say they took any exam. You know, it's kind of silly. And he tried to emphasize to me that if students are feeling a little overwhelmed, that they shouldn't take the exam. Unfortunately, I don't think like that message has kind of reached the general student population, because I feel like a lot of students are still feeling some type of whatever pressure it is, right? The fact that maybe that most of my friends are still taking the exam, I should take it too. Maybe they're afraid like if I don't take the exam, it'll look bad in like whatever way, some nebulous, like it's not gonna happen, right? So just know when you take the exam, I would look at it as an opportunity to have fun, to kind of exercise. For those of you who are taking the exam, which I know is most of you, I would look at it as an opportunity to have fun. I feel like physics and at the end of everything should be fun, right? It's like, oh, it is fun to try and explain why something happens. These problems can be kind of like a puzzle, but that's the way you should look at almost everything. I think life is a game. Anyways, so let's look at this problem, right? Yeah, I don't know why, because I feel like a lot of the language exams are the ones that are the most valid. Anyways, cool. So here we go. I'm going to pull this up, the problem. I am going to make it so I can see everything. All right. So some of you have looked at the problem. Some of you have not. Okay. If you have not, I would recommend that you kind of like tune out right now. Try to do the problem yourself, time it or not. I don't really care. And then look at this a little later, okay? Because I'm just going to spoil everything. All right, so I forgot one little thing. Here is theta, okay? And this is theta naught. I know I've spoken against previously doing a targeted AP review because I disagree fundamentally with a lot of things about the College Board and the exam. But after looking at this problem, I do think it has a lot to teach you, independent of the fact of whether or not you're taking the exam. So I think this is like an extremely good review for a lot of things. It's a problem that combines a lot of things. And that's why I think I want to take the opportunity to review it. Okay? So student one, all right, so here's the introduction to the whole thing, right? There's a pendulum, it's rotating, it makes a circle of radius r around the point center C. So the ball and the point C are always going to be on the same plane, right? And it's like a piece of paper that's like on this thing, right? So it's like the same as this book, and it's always going to be in the book, right? It's made up of a string of length L, and it has a mass M, and while it's making the circle constantly, it's making it such that the string always makes a constant angle of theta naught around the vertical line, right? So it basically makes a cone. This is known as a conical pendulum, right? As the students are discussing the motion of the sphere and make the following statements, right? Student 1 says, none of the forces exerted on the sphere are in the direction of point C, the center of the circular path. Therefore, I don't see how there can be a centripetal force on the sphere to make it move in a circle. So here's what student 1 says, right? Student 1 basically looks at a free body diagram and says, oh, FG goes here, FT goes here. If FC always points towards the center, right? He says there is no FC because the only two forces acting on the ball don't point towards the center, right? So because FC has to point to the centripetal force has to point towards the center, and there is no force that points towards the center, the student is saying that there is no centripetal force, right? Here's what student 2 says. I see another problem. The tension force exerted by the string is at an angle from the vertical. Therefore, its vertical component must be less than the weight mg of the sphere, right? So here's what student 2 says, right? Student 2 says, if this is Ft, right? And then this is Fty, right? And, we can go ahead and say this is actually equal to Ft cosine theta. Whoa, whoa, whoa. Whoa, whoa, whoa. Time out, everybody. Someone put it in the chat. Why am I using cosine theta instead of sine theta if this is a vertical component? What the heck? What? Isn't that weird? Isn't the horizontal cosine and the vertical sine? Why am I using cosine theta here to do my y component? What the heck? Chris says we're using a complementary angle. There are many different ways to say this. Just because Chris said it, I want other people to participate too, right? What's another way of saying complementary angle? And I actually don't prefer that kind of terminology. Why am I using cosine? Here we go. If that's theta, that's theta. And I'm really looking at this line. I'm looking at this triangle, right? And if I want to find, if this is my hypotenuse, this is my adjacent side, and this is my opposite side, right? Chris again says sine theta is the horizontal component of theta. Yeah, but I'm saying why, right? And it's a simple trig problem, right? Because my theta is relative to the vertical, the opposite side is actually the horizontal side. And that's the side like SOHCAHTOA, right? If I'm going to use Hello? Right, sine is always talking about the opposite side. So, right? So, if my angle is here, the opposite side is here. So sine is this one. It's going to be this one. Cosine deals with the adjacent side, so it's always this one. The reason why it's almost 95% cosine is the horizontal, sine is the vertical, is because 95% of the time we're given an angle relative to the horizontal, right? But this time we're actually given cosine relative to the, theta relative to the vertical. All right, but anyways, let's go back to what student 2 is saying, right? So student 2 says, oh, because FTY is less than FT, right? That means FG is going to be more than FTY, which means there's a net downward acceleration for the thing. All right. So both of these students give two different arguments for why it's not going to be in uniform circular motion, right? Because student 1 says there's no centripetal force because there's no force acting towards the center, therefore it can't be in uniform circular motion. Student 2 says there's the net force actually points down, so there's no way for the net force to point towards the center, and therefore it's not going to be moving in a uniform. They're both wrong, right? And student 3 comes up with two different equations, right? The first one being F net equals Ft R over L, okay? And this is 3A, this is 3B. Okay. And the second equation is that Mg is equal to Ft times the square root of L squared minus R squared over L squared. Okay. And freeze. Okay, so here is part A. What's one aspect of student 1's reasoning that is incorrect? I would argue that, so you have to really, to answer these types of questions, I would highly encourage you, like immediately, you're always going to see like what's right and what's wrong because you know what's right? You've done these problems a lot before, okay? But I would argue that it's more important to like actually look at their argument and look at their implied premises, okay? So what's student 1's implied premise here? I basically spelled out their argument, right? Student 1's argument is saying, for there to be a centripetal force, there needs to be an actual force pointing towards the center. Why is that wrong? Because it's not. The centripetal force is not a type of force. It's simply the net force. It's a re-expression of the net force. So for part A, I would answer student 1 is incorrect in assuming that the centripetal force has to be one of the two forces acting on the object, when in reality, it'll be the vector sum of the two forces, tension and gravity. Not tension or gravity. It's actually the sum of tension and gravity. And there is a possibility that Ft plus Fg, these two vectors actually add to a force that actually points towards the center. So they're incorrect. Student 2, this is part B, all right? Student 2, I would say, let's take a look at what they're saying. They're saying this Fty is less than Ft, therefore it's less than Fg. So what's the implied premise the student's making there? The implied premise the student makes is that Ft, that the tension equals the gravitational force, right? So this student automatically assumes that the two forces cancel out, or not just cancel out, but that the tension is equal to the gravity. And because this component is less than the tension, then the student says, then since these are equal and this is less than that, then this has to be less than that too. And that allows the student to conclude that Fg is less than the vertical component, and there's a net downward force, right? So you would say the student is incorrect in assuming that, right? The student is incorrect in assuming Ft is less than Fg. And in actuality, when this circle is actually moving in a horizontal circle, there is no vertical acceleration. And actually, I know that Ft is equal to Fg. And I use the reverse reasoning to say, because Fty is equal to Fg, why do I know that? Because there's no vertical acceleration, that I can actually conclude that the tension is actually greater than the gravitational force, right? It's actually, the student has it like completely backwards, right? Yeah. So for student 1 and student 2, I would not talk about like what's actually true, right? So the trap for part B is say, actually they're equal because there's no vertical acceleration. We don't know that, right? So instead, you want to like build their argument and look at the premises like about which they're like building their arguments and their reasoning, and you say, oh, what the student actually is saying is that tension is greater than or equal to the gravity, and that's not true, right? We actually know that's not true, right? Okay. Now let's move on to part C, which goes on about these two, C and D, where I talk about these two equations and how they can be used to disprove either student 1 or student 2. All right. Already here, you can rewrite these using trig functions. R over L is sine theta, right? So this is F net equals Ft sine theta, which is actually equal to Ftx, right? So the equation 1 basically says the net force is the horizontal component of tension. Okay, Sarah, why are you confused? Okay, so moving on with part C. And Sarah, I would ask what the question was, but I just feel like for those students who are not tuning in live and seeing this later, I just kind of like want to move on just for them. All right, but tell me later. Or actually, why don't you just put it in the... do you have any... No, whoever you are, Ubul Sadek, that just goes with experience. Yeah, you want to say like, well, a way to recognize that, I think, would be just to verify if this is true or not. How do I know this is true? What I do know is that when I make this free body diagram work actually, right, I know it's Fty and Ftx. And I know that, oh, like in real life, if I'm actually solving this, and I know it's perfectly horizontal, which is actually stated in the problem, right? I know these cancel out because there's no vertical acceleration. And I know the net force is just Ftx. And I know Ftx is going to be Ft sine theta. And then I look at this equation. Well, they're saying, well, what I know is F net is Ft sine theta. And what this equation is giving me is Ftr over L. Why is it shown that way? The more you think about it, you should see, oh, they're the same thing. Because what is sine theta? Oh, I could actually plug in the theta into my calculator, But if they're actually giving me L and R, I can solve for sine theta using L over R as well, right? So it's just, yeah, you have to recognize it quickly or not, right? And then this one, the square root of L squared minus R squared, you can kind of clearly, what is, oh, that's this, right? Let me call that H for height, all right, not hypotenuse, right? So this is H over, this is H over L, okay? Not squared, sorry. And that is actually equal to Ft cosine theta, right? Because this is equal to Ft and then H over L. And then that's equal to Fty. So I think it's clear to see that this equation counteracts the second student, right? They're saying, no, there's not a downward net force. Actually, the y component is equal to gravity. That's what they're saying right here, right? Fty equals mg. So that kind of corresponds. And so how would I explain this really quickly? I would say L squared, the square root of L squared minus R squared over L is actually another way to write cosine of theta naught, and cosine of theta naught multiplied with Ft actually just gives you the vertical component of the tension. And what this equation really says is mg is equal to the vertical component of tension, which directly contradicts student 2. How does this formula directly contradict student 1? Well, they're saying that they're talking about the net force, right? And that's exactly what we're getting at. It's the net force is Ftx, and because the net force is in the horizontal direction, this ball is actually accelerating in the horizontal direction, so it can be So while neither of the forces point in the horizontal direction, their resultant sum does, and that allows for the possibility of a particle that would accelerate towards C, because that would have to be in the horizontal plane. Right? Cool. Now let's move on to E and F. Okay? E and F are probably my least favorite parts of this. So they say, hey, as I increase the V, R increases. You guys, I mean, you see this all the time, right? Like, let me see, do I have anything I can like swing? Oh yeah, my hashtag Bronx Science, right? Am I right? All right, so you guys know that like the faster I spin this, right, the larger the radius becomes, right? We did a lab about that, right? The conical pendulum lab, like this one. Whoa, yeehaw! Yeehaw, I live in a state that's ending their lockdown early. Okay, cool. So, and they model their, well, since they make that observation, right, they choose to model R as a function of V to be R equals V times the square root of L over G. Okay, so this is super weird. I'm actually going to answer part F first. Anytime they ask you, right, regardless of if it's correct, regardless of the correctness, right? Anytime you see this, you should automatically do a couple things. You look at the extremes, right? Look at like the really small and large values and see if it makes sense, okay? And that's what I'm going to do for part F. So as V increases, R increases, right? I see this, right? This is slow, this is small r, right? And the faster it is, the larger it is. And one thing you should note is that as I increase the speed, there's a limit to how big r is. What's the maximum value of r that you could ever reach? The maximum value of r, right, is L. And that happens when L is super flat. It's like perfectly horizontal, right? So the problem with this equation is that it implies that R increases linearly with V. And as soon as V becomes greater than G squared L, right? R is going to be greater than L. And that's a problem. So all you have to say for this problem is that, no, this thing sucks because for a very large value of V, R is going to be greater than L, and that's physically impossible, right? It doesn't matter if L is constant or not, Demon. Like all I have to see is as soon as V is greater than this, R is going to be greater than L, right? So that's a really big problem. So it's not plausible. Sometimes you're going to have to look at the reverse, like for really small values. And for really small values, this makes sense. If V is 0, R is 0. That makes sense. V 0, R 0. That makes sense, actually. So whenever they ask you to look at, regardless of whether it's correct or not, is it plausible, look at the two extremes. And both extremes have to catch up. So if I say, oh, look at V is 0, R is 0, that makes sense. Cool, it checks out there. But where it doesn't check out is the other extreme, where V is really big. And that gives me an R that's bigger than L. Okay? Now, just by answering F, right? No. Big V implies R is greater than L, and this is impossible, right? You've already answered E. So that to me is where it's really weird, okay? So maybe like another correct answer for E would be like, yeah, because as V increases, R increases, and that's what they predict. Dumb, all right? So I don't like that interpretation of E, but the fact that they give it as two separate problems kind of suggests to me like that's the answer they're looking for. Never think about what they're looking for. Just answer to the best of your ability. I would answer F, and then for part E, I would just repeat everything you wrote in F. But I would also include while E, you can answer yes and no. It's plausible in that R increases as V, just like they predict, but it's also implausible because it predicts that eventually R will exceed L, and that's impossible. Okay? All right. So now we get to the second part, okay? And instead of doing a conical pendulum, they actually just straight up make this thing go in a regular pendulum. Okay, and this is theta max. Okay. All right. And it goes back and forth like this. And instead of moving in a horizontal, okay, the graph below shows the data for the square of a pendulum period as a function of string length L, right? And they have t squared, and they have L, and it's a line. You bet your bottom dollar it should be a line. Why should it be a line? Because I know actually on your reference table, this is the formula for the period. It's a square root curve, which means t squared equals 4 pi squared L, and then G is here. So t squared and L should give a line, right? This is back to our linearization review. This is why I like this problem, right? Because it does really touch upon everything we learned, which is kind of cool, right? Only 4 LOLs, huh? -1. Okay, so you bet your bottom dollar I should expect a line, okay? Now explain how the graph would change under the following circumstances. If the mass of the sphere is increased, justify your answers. All right, so immediately you should say, oh, this graph kind of confirms that there's a linear relationship between t squared and L, and actually the very formula it confirms is this one from our reference table, all right? And from this reference table, you can see the mass is not anywhere on there, okay? So for part G, I can say, because mass is not in this equation, we also know the period of a pendulum is mass independent. G would have no change. The maximum angle is decreased. Again, theta is nowhere in here, should have no effect. Okay? I, the pendulum is taken to the moon. Aha! This does change the period. But remember, we're not talking about change in period, we're looking at the graph itself. So if I go to the moon, that means G decreases. But that means this number, 4 pi squared over G, increases. What is this? Oh, this is the slope of the graph, right? So it should change to this, right? It just gets steeper because decreasing G will increase the slope of this graph, right? Okay. J is cool, all right? The graph above shows an angle theta. Okay, and I'm going to draw this here. Angle theta time. So the period is actually 1 second. That's pretty cool. Okay, and it looks like cool. So it's like a perfect cosine graph. Awesome. Do you need to know its cosine? No. Okay. The graph above shows the angle theta from the vertical as a function of. Explain how this graph shows evidence of a net force acting on the sphere, and how it shows that this net force is a restoring force. Okay. Wow. Take some time to think about this. I mean, it's pretty hard. And my way of explaining this is purely using kinematics, right? Theta is a different way to look at position. So it's almost the same as x, all right? And I actually know x is just equal to r times theta, right? So it's just a constant times theta, right? And the reason why I know, let me give you an example. When can I say there's no, what does a position versus time graph for an object look like if I don't have a net force? There's two options, right? It's either always going to be at the same position, no acceleration, or it has constant velocity, right? And constant velocity means I have a constant slope, all right? So this is an example, this is an example. All three of these are examples of what a position versus time graph can look like if I have no acceleration or no net force. So compare that with this. Why do I know there is a net force? Because it's curvy. Because it's curvy, I know my velocity's changing, right? Initially here, I'm at rest, and now I'm speeding up. And then I'm slowing down, and I'm at rest. And then I'm speeding up towards the positive direction. And then after I hit this point, I start slowing down, right? My speed is constantly changing because the slope of my position versus time graph is always changing. And that's why I can say that there's an acceleration, and that's why I can say there's a net force, because F net equals ma. Now, why do I know that this net force is a restorative force? Remember, what is a restorative force? A restorative force is always a force that points towards equilibrium. And check me out, check me out. Is my acceleration negative or positive? Here, it's negative because my slope gets more and more negative. Is my acceleration here positive or negative? It's positive because the slope gets less negative and then more positive. And then here, is it negative or positive? Well, it's negative, right? Because it's decreasing in positivity, right? Another way you could look at it is frowny smiley, right? My second derivative, or my acceleration, is always negative if my position graph is frowny. So it's frowny here and it's frowny here, so I have negative acceleration there. It's smiley here, so it's positive. And what does that mean? When I have a positive displacement, my acceleration is negative. When I have a negative acceleration, my acceleration is positive. So this means when I'm in a positive position, my force or my acceleration points negative, right? And when I'm in the negative displacement, my acceleration or my force points in the positive direction. So it's always pointing in the opposite direction of my displacement from equilibrium. And that's literally the definition of a restorative force, all right? Please let me know if you have questions for that, okay? I'm gonna heat my water for one last steeping for my pot of tea. Okay, so there are no questions for that. Let's move on to the last part. Yikes. Okay, it's one of my least favorite part of the problem. Okay. Unfortunately, the ball does not simply do, let me see, it's not just doing this, right? It's not. It's doing this. So it's actually rotating a little bit. It's not just translating, it's rotating, right? If you made a camera just focus on the ball, it would look like this, right? So it's rotating. Which means if, not only that, it's changing, right? Here I have clockwise rotation, counterclockwise rotation, right? And so I have omega is changing. So there is a torque. Okay? And they're saying, hey, when the sphere is at the maximum rightward displacement, so when the sphere is here, where does torque point? Okay. There's two ways to look at this. One is to look at the torque. Okay, so the first way is using kinematics. Right? And here's what I will say. So right here, omega is 0, right? Right there, it's 0 because it's changing direction. It's not spinning, it's completely at rest. But right before, where was it spinning? Right before, it was spinning in this direction, right? Whoop, right? And they even draw the diagram to help you out, okay? So right before, it was spinning in this direction. So omega points out of page. And right after, it's now going to start going clockwise, right? Clockwise, and this is counterclockwise. So this is into the page. So where was the torque pointing the whole time? If before I'm here now, the torque or alpha or both, right, had to have pointed clockwise, which is into the page, right? Because torque or alpha, right, is really equal to change in omega over change in t, which is omega final minus omega initial over change in time, right? So omega final was clockwise, omega initial was counterclockwise, minus a counterclockwise is actually plus a right? It's actually a clockwise plus a clockwise. Yeah, so that's one way to think about it. You should say either. Either is fine. Into page or clockwise. The other simpler way, but the more dangerous way, okay, is to actually look at the torque. This is dangerous because if you choose the pivot to be the ball, then you're left with no answer. Gravity, tension. There's no torque because the R here is 0. The R here is 0, right? Both those forces are acting right on the pivot, so they don't put a torque on the ball, which is really, whoa, but I thought there is a torque. Yeah, there is a torque. You just chose the wrong pivot. The pivot you should choose is here. And now there are two forces, right? There's a tension force and a gravitational force. The tension force offers no torque because it's parallel to R. But the gravitational force, once I take the perpendicular component, right, this is Fg perpendicular, right? That force exerts a torque relative to that pivot, and it's going clockwise. It's going clockwise or into the page. Notice my thumb is pointing into the page. Great. Well, what's the difference between these two? My pivot or reference point is stationary, and it's not accelerating, blah, blah, blah. That's really important, okay? when you're looking at the torque on a system, you need to be able to look at it from a stable reference point, which is why this fails, right? So if you were to look at it from, oh, where's the net torque point? Maybe I'll just look for the net torque, like this. And I can look at the torque due to tension, the torque due to gravity, the torque due to tension 0, the torque due to gravity is clockwise, so the net torque is clockwise. The danger with that is you need to choose a stable pivot. Okay? So I choose this one. Okay. That's the only part of the pendulum that's not moving, actually. Right? Okay. If you're still a little confused about how that works and stuff and like feel a little iffy about it, then this one is so much cleaner. Right? It's just looking straight at kinematics, right? Which I think is kind of nice. And there you go. That kind of wraps up problem number 1. Tomorrow we will be going over problem 2 and doing a more extensive review on conservation of energy as a whole. Okay? And then Wednesday we'll go over momentum, linear and angular. And that should be it, right? We won't have class Thursday. And I want to give a very short waves assignment that's due Friday. Okay. Yeah, so it's a light week. Take it easy. Love you guys. Relax. Please, please, please. I know I sound like a broken record. I know it can get a little annoying, but please do not stress about this. Easy for you to say, Mr. So, you're not a student. Just have fun. Wasn't this fun? Just have fun. And if you don't know how to answer something, whatever. Just be like, wow, I have so much to learn. Do you know how boring life is if you know everything? I don't know. Why don't you ask? Don't. I wouldn't know, right? It's so life is more fun if you like don't know things and if learning, right? And if you're on the exam and you don't, there's a part that stumps you like this, right? Like, or part E, I thought was very confusingly worded. Whatever. This is more stuff to learn. How beautiful is that? Okay, so have fun with the exam. Please treat it as an opportunity to show how much you know. And if you end up getting stumped, just know it's not a perfect indicator of how much you know. As taking this practice exam should have shown you, right? Like, I definitely have students that know a lot that kind of get stumped with these types of problems. Some of my best students last year who have a really great understanding of physics, like got a 4. They weren't the ones to get a 5. Who cares? They know they're in my top 34. Nothing can take that away from them. And, you know, it was just a weird exam that year, or maybe like they just answered it in a way the graders weren't looking for. Okay? And a 4 is great. But what I'm saying is like you would expect the best to get a 5, right? And like they didn't. And who cares? Right? Who cares? Please don't put any weight on this. If you get a 5, great, right? Like I would say you did well in spite of the circumstances. What are the circumstances? Like it being probably a really time-crunched exam, it like you like suffering under remote learning for 2 months before the exam, having a teacher that really doesn't care about the exam. Like if you get a 5, you did it in spite of all those things. Yay. And if you don't, And if you get like a 3 or below, who cares? I still love you. You're still in my top 34. I'm still gonna go on the record saying like this is not a great exam of like really showing or measuring how much you really know. So it's okay. Just have fun. All right, and we're gonna have fun tomorrow, okay? Because I just looked at both of these problems this morning when I woke up at 9, and problem 2 also looks to be a little bit of fun. Right, so we're gonna have fun tomorrow. And you know I love conservation of energy, and that's what we're gonna go over tomorrow. Yay! Okay? Don't stress. Uh, then just say into the page, don't think about what they accept or not. I don't care. Okay? No, they would accept into the page, I promise. Say using right-hand rule into the page. That's more correct than clockwise and counterclockwise. Objectively so. Okay? All right. Have a great day. I'll see you tomorrow. Okay? And keep it positive. All right? My top 34 students.